Howdy, howdy, this is Mr. Potter. What we're going to talk about today is a culmination of what we've been doing the previous couple of days. We've been talking in particular about a couple of algorithms. We've talked about the idea of how to find the minimal spanning tree with Kruskal's algorithm, and we've also found the shortest path from a source to its clients based on Dijkstra's algorithm. And the idea here is we want to talk about how do we set up our network so that our network can learn, so that our network can evolve. Because to be quite honest, if I'm a computer on the network, I don't have a snapshot of the entire network in my mind at any one particular second. Because new computers come on the network, old computers go off the network, network connections may be completely disconnected by infrastructure issues, maybe a hamster is bitten through a wire at some data center, maybe a data center has installed new lines because of high demand, maybe a data center has taken away some lines because there just wasn't enough demand or they couldn't afford it. The internet as an object tends to be in flux, and so our routers have to be able to adapt, because what may have been the shortest path to a server before may not be the shortest path later on. And so the idea here, because the internet is fluid, we need to look at what some of the things we're talking about. So for us, our nodes that we've been talking about are other routers or servers. The edges that we've been talking about are the connections. In other words, the wires that connect these computers together. And when we talk about the cost, we're really talking about the milliseconds to transmit a packet. So we're talking about how long it takes to actually transmit a packet from one router to another using these connections. And as a user of the internet, I want that time to be as short as possible. So I need to make sure that my computer, that my router, or the servers that it connects to, adapt and learn and update, so that what was an efficient path, as soon as it becomes an inefficient path, my server is trying to find a more efficient path later on. So I've got a brief illustration of the network. This is my internet here. Something that you should notice is that computer A, which I've got here, only has 3 connections. It only has a way to get from A to D, from A to B, and from A to F. There is no way to get from A to C, and there is no way for me to get from A to E. So I'm going to have to ask those servers near me what's the most efficient way to get from A to E. Maybe it's by going through B, maybe it's by going through F, maybe it's by going from A to C to F to E. There are a lot of different paths here. One of these paths may end up being the best path, and my job is to find this. So I'm going to poll my neighbors and ask them what's the most effective way to get to certain places, and they in turn will ask as well, so I'll be able to update my answer as time goes on. So as you notice from our diagram, each server has a limited number of connections. Each server isn't connected to every other server on the internet, and that's the way it is in real life as well. So what we have to do is we have to find the most effective way, the most cost-efficient way, the fewest milliseconds to get to any point on our network. So what we have are something called router tables. In other words, server A is going to keep track of all the ways that it has to get to the different places. And server B will have to do the same thing. And server C will have to do the same thing as well. Now keep in mind that A can always transmit to itself with 0 milliseconds of time, similar to B, similar to C. But if A wants to transmit to B, A is looking at B and sees, oh, it takes 18 seconds or 18 milliseconds to get a message from A to B. B notices the exact same thing as well. A has no way to get to C, but B has a way to get to C. It takes 9 milliseconds, as does this. And of course, A has a way to get to D, C has a way to get to D, B does not have a way to get to D. So for A takes 2 milliseconds to get a message to D. C takes 8 milliseconds to get a message to D. And then if I'm looking at A has no way to get to E, B has a way to get to E. B is going to take 3 milliseconds, and C has no way to get directly to E. And similarly, A has a way to get to F, 4 milliseconds. C has a way to get to F, 7 milliseconds. And B doesn't have a way to get to F. So what happens is, for this first iteration of our router tables, this is what our router table looks like. Now, A has a direct connection with B. So A can actually ask B questions. So what A can do is ask B, hey, B, how do you get to C? Because B has a way to get to C. A doesn't have a way to get to C. That's currently blank right now. But if B says, oh, it takes me 9 seconds to get to C, then A can say, oh, that means it takes me a total of 18 plus 9, or 27 milliseconds to get to C. Similarly, A can ask D, hey, how do you get to C? And D will tell it, oh, once you get to me, it only takes 8 milliseconds. Well, this 2 and this 8 is a much better time to get to C. So A is going to forget about this 27 milliseconds and say, hey, you know what? This 10 milliseconds that I've got going from A to D to C really is the best deal that I've got going. Now, similarly, B can ask how to get to A, because B is going to ask how is it going to get to D, because B has no connection to D. So B will ask its neighbors. B will ask A, hey, how do you get there? B will say, oh, 18 plus 2, which gives me 20 milliseconds. It'll ask C how to get there. It's going to say, oh, 9 plus 8, which is 17 milliseconds, and that 17 milliseconds is the best way. And so what's going to happen is that these times are going to be updated by each server asking its neighbors what the most effective way is. So again, A has no idea how to get to E, but A knows that it can ask D how to get to E. That's going to be 2 plus 6, or 8 milliseconds. A can ask B how to get to E, 18 plus 3, which is 21 milliseconds, not good. And A could ask F, and F would say 4 and then 3. Oh, that 7 milliseconds is a much better time. So what happens is each of these routers will ask its neighbor, and each of these neighbors will in turn ask its neighbors, and these numbers will actually get updated. So for example, B has a path to D, but B could also ask someone else how to get to D. B could say, oh, it's 3 seconds to get to E, and then 6 seconds to get here. This 9 milliseconds, by going from B to E to C, is a much better time. And so the idea is, by repeatedly polling the neighbors, and after it's asked the neighbors, asking the neighbors again, because maybe the neighbors have found a more efficient way to get there. That's really how routing tables work. The internet evolves, the internet adapts, and if a wire were to suddenly become snapped, and all of a sudden A couldn't get there in 7 milliseconds anymore to E, A has other paths, like this 8 millisecond path to get A to D to E. And A always has another path. It could go A to B to C to D to E. It's not the most effective path, but it is a way to get there. And if everything else crashes, if everything else falls apart, the idea is that the internet has redundancies built in it to make things work, to make things connected. So that's how router tables work. It uses a combination of these techniques. It's not pure Dijkstra's algorithm, because all of these are senders, not just one. I need to keep track of how all of these adapt as time goes on. And it's not just finding one best path, because notice that A to F is a pretty good path, but there are other paths. We need to find the best path, but the best path could change as time evolves. So, once again, this is Mr. Potter. Thank you for watching. Have a great day.